Non provo a scrivere, vediamo se si vede. Si vede quello che scrivo?
Sì, sì, prof. Per ora sì.
Per ora sì, ok. Però sto pennarello non mi sta piacendo, vediamo. Cioè, più vivace. Questo forse più grosso. So, last time using the Grand Canonical Ensemble, we derived the Grand Canonical partition function for a free gas for a gas of 3 fermions and 3 bosons. And I remind you that the reason for dealing with the Grand Canonical Ensemble was to relieve the constraint on the conservation of the number of particles, because that was making the calculation of the canonical ensemble particularly difficult for the combinatorial. Okay? Whereas in the Grand Canonical Ensemble, we do not have this constraint, so everything is easier. And we derived that the Grand Canonical partition function can be written for bosons as a product over Q, where Q is the momentum of the particle, 1 divided by 1 minus fugacity, and e to the minus beta epsilon q, where epsilon q is h squared q squared divided by 2m, and is the kinetic energy of a particle having a wave number k. And now here there is a product because we have quantization of the wave number, because we are using the box, the normalization of the wave functions in a box. Okay? And z is the fugacity, and it is equal to the exponential of mu, which is the chemical potential, times beta. Okay, so now we can start by deriving thermodynamics. And the first thing that we can try to write is n, which is the average. Let's indicate with the, so let's compute the average number of particles that actually in thermodynamics we just indicate with n, not make any difference because we are neglecting completely fluctuations. But this was derived in the context of the Grand Canonical Ensemble as a derivative of the partition function. So in particular, this was the derivative with respect to z of the log of the Grand Canonical partition function. Okay. So I take this quantity, I make the log. When doing the log of a product become a sum of log. And then I have a minus here, so it should be written as minus z sum over q of the log of 1 minus z Si vede ancora quello che c'è scritto? Sì, forse sì. Adesso passo all'altro, poi andrò sotto a litigare come al solito. Okay, so I have the derivative of the sum of the log Okay, so I can continue with this calculation. So I get minus z. Then I have the sum of over q. Here you have 1 minus z exponential of minus beta epsilon q. And I'm deriving this with respect to z, so I should have minus exponential of minus beta epsilon q. Ok? Meno z, quello là, va bene. Okay, this is equal, we can work out a little bit this expression. This is equal to the sum over q of, let me multiply by e to beta epsilon, numerator and denominator. And let me also, me la faccio da derivo rispetto a quello. Sì. Ok, let's do it. So this is z, and here I have e to beta epsilon q minus z. Then let me divide the numerator and denominator by z. So equal also to the sum over q of 1 divided by e. Z to the minus 1 is exponential of minus beta mu. Therefore I get beta epsilon q minus mu minus 1. Okay, which is the average number of particles, which is a sum over q of this quantity, from which you see that you recognize a result that you already know, which is the distribution, the Fermi and the Bose-Einstein distribution, or the Bose-Einstein statistics. Which tells us that if I fix Q and I ask myself which is the probability of occupying this state, or the number of particles, better to say, in this state, so the average and Q, well, this is equal to 1 divided by e to beta epsilon q minus mu minus 1, okay? Which is the standard distribution of Bose-Einstein. Qui non c'è bisogno che la racconto troppo. So here this is the version, well, this is the Bose-Einstein distribution, and this is the number of particles where I'm summing over Q. Now, if I want to make calculation easier, usually I go through an integral, which so from discrete to continuous, I go from a sum over Q to an integral. We have done this already several times, in which I have to integrate over dq, multiplied by the volume, and divide by 2p to the power of 3. Okay, so this we have used also last time. Therefore, if I want to write the average number of particles or the number of particles in terms of an integral, I have to do this. So, which was the average number. At some point, I will remove this average number of n. Is now b divided by 2 pi cubed integral over dq of the quantity that I had here, which can be written by considering spherical symmetry. So let's consider spherical symmetry already. So to have a final expression, I have here 4 pi coming from the solid angle integral. In the denominator, I have 8 pi cubed. So therefore, I will have 2 pi squared left. Then I have dq and q squared divided by e to beta epsilon q minus mu minus 1. Okay. From which I can also get the density of particles, because I divide by the volume. And so the density of particles is given by 1 divided by 2 pi squared and integral over dq of q squared e to beta epsilon q minus mu minus 1. And this is the relation that provides me this is an equation that provides me the relation between mu and number density. Lo stimicidio di Pennarelli.
Scusi, prof, riesce a mettere un po' a fuoco perché non so se è un problema mio di connessione o...
No, ma è il pennarello, secondo me. Now you see, beh, si vede un po' meglio quello che scrivo?
In rosso sì, un pochino.
Sì, stanno morendo tutti. Sorry. I use this one and then I go downstairs, okay, to take some others. Okay, so this is the relation between chemical potential and density. Now we can also, to complete the picture, we can compute in the grand canonical ensemble the pressure as a function of the other quantities. And this was the second equation of the grand canonical ensemble, that was telling me that P times V divided by KBT, this is the log of the grand canonical partition function. Okay, so in the case of a free, so a classical gas, this will just be n. Okay, now we do as before. The log of z of g is a minus sum over q, and here you have the log of 1 minus z e to the minus beta epsilon q. Okay, so this is the relation, well, this is the pressure times volume, which in the continuum becomes, as before, we substitute the sum with an integral. Okay, now it's out of focus. Vediamo se si riprende. Now it's completely out. Sì. Che lui cerca qualcosa su cui focalizzare. Forse. Chissà come funziona questa cosa. Ma infatti, bisogna solo aspettare. So let's wait. Ma se io mi muovo è meglio o peggio? Boh, chissà. Ok, now it's coming. Più o meno.
Prof, penso che il problema è quando si avvicina troppo alla fotocamera, perché li cambia il piano.
Quando mi avvicino io, ok. Così.
Adesso è a fuoco.
Adesso si vede. Bene. I go to the continuum, and therefore, as before, here I have a minus v divided by 2 pi squared, and then I have to integrate over the q. Okay, maybe I forgot before, but it's from 0 to plus infinity because we are in spherical coordinates of what q squared is left, and then I have a logarithm of 1 minus z into the minus beta epsilon q. Okay, this is in the continuum. Vediamo se è tutto giusto. Okay, from which I can derive. So this is PV equal to K divided by KBT. The volume drops, and therefore I have a pressure divided by temperature, which is provided by this relation. Okay. So this is, if you want, this is the equation of state. Whereas the relation that we had before provides me a way to link the chemical potential and the density of particles. Now we can go on and we can compute, for instance, the internal energy, U, is a minus derivative with respect to beta, as in the canonical ensemble, of the logarithm of G, where I'm deriving with respect to beta. Keeping, let me write here, keeping Z and B. Okay, it's a little bit tricky, but one can show, and I think I have not done this in the grand canonical ensemble, but that the grand canonical ensemble, the independent variables are the fugacity, the temperature, and the volume. And similarly to the canonical ensemble, but the interpretation will be clear in a moment, I can derive the internal energy by doing a derivative with respect to beta of the log of Z of G, by fixing Z and B. Okay? So let's try to do it. I have to take the expression that I had before, which is this one, and derive with respect to beta. So then U will be, so here I have a minus derivative with respect to beta. Here there was a minus, so I have a plus. V divided by 2 pi squared, which is still there. Then I have integral from 0 plus infinity, dq squared. Okay, I have to derive this guy here. So I have 1 over z, and the denominator 1 minus z e to the minus beta epsilon q. Then I have a minus z e to the minus beta epsilon q. And finally, I should have a minus epsilon q. Okay. So then U is equal to V divided by 2 pi squared, integral from 0 to plus infinity dq squared. Epsilon q is still there. Then I multiply by e to beta epsilon q, and I divide by z, and then I should get, as before, divido per z, sì. So e to beta epsilon q minus mu minus 1. Okay, where the interpretation now is very clear in the sense that this was this guy here was present also in the calculation of the number density. Then I multiply by the epsilon q. So then this is, if you want, the distribution, well, the probability, the occupation number of a certain state q multiplied by the energy of the state, and I'm summing over q, which is a reasonable definition, or is a reasonable formula for the internal energy. Okay. So I take the same the same distribution that I had for the number density, but I multiply by epsilon q, and it provides me the internal energy. Now let's notice one thing, which is actually very important. It's very important because, as we will see, it will lead to the Bose-Einstein condensation, which is the following. For instance, let's consider the logarithm. So this is an important note. This is rather important because it will lead to the actually to the Bose-Einstein condensation. When passing from the discrete to the continuum, actually we are making something which is a little bit dangerous, because consider that log of z of g, that was minus the sum over q. This was the initial expression of the log of 1 minus z exponential of minus beta epsilon q. Now you see that here this expression could diverge in the case in which epsilon q is equal to 0. So if epsilon q is equal to 0, and this is a honest value for q, which is q equal to 0, and z equal to 1. In this case, the exponential is 1, this is 1, and then I have a logarithmic divergence. Okay. You will see that this divergence, actually, it's a pathology that comes from the fact that we are passing from the discrete to the continuum in a way that is not very careful, and actually there's no divergence in a real system. And this divergence is telling us that actually it is possible in this condition to have a finite occupation number for the ground state. Okay, so what is this epsilon q equal to 0 is the ground state energy of a particle, so having momentum 0. Okay, so when doing this calculation, when passing from the discrete to the continuum, I have to be careful. And actually, the best way to do it is to separate the contribution that I have here from the epsilon q equal to 0. Okay? So, scriviamolo qua. So to single out the divergence, okay? So let me write it in this fashion. When passing from discrete to continuum, let us separate the epsilon q equal to 0 contribution okay, because this one is the one that can lead to a divergence. Okay, so when doing that, questo sembra molto, proviamo col nero, So when doing that, I just need to modify the expression as I had before for the pressure and for the density as follows. So the PD divided by KBT, this was just the logarithm of the grand canonical partition function, and this is equal to minus V as before, divided by 2 pi squared integral 0 to plus infinity Q squared logarithm of 1 minus Z e to the minus beta epsilon Q as before, which is the continuum. But let's separate the single point associated with the epsilon Q equal to 0 in the sum, and therefore I will have a minus log of 1 minus Z. Okay, this comes from epsilon Q equal to 0 in the previous sum. Okay, so you see that here I have isolated the divergence, the logarithmic divergence, by basically taking outside the sum, the Q equal to 0 term. Now, of course, this is a matter of an integral, so the integral doesn't care about epsilon Q equal to 0 because it's just 1 point. Okay, so it's a null measurement set. Okay, so when doing this integral, if I separate the contribution from epsilon Q equal to 0, it doesn't make any difference. Okay. And similarly for the density, I have an expression which will be the continuum, which as before is this quantity, dq squared e to the beta epsilon Q z to the minus 1, where this is exponential of minus beta mu. Okay. Plus, again, it does separate the epsilon Q equal to 0 contribution. And if you take the expression that we had before, che stava all'inizio, yeah, so the sum of 1 divided by e to the z to the minus 1 epsilon beta mu minus 1, and you take this expression, andiamo alla pagina 2, adesso siamo alla pagina 3, and you get 1 over the volume, as it should be, 1 over the volume, and then I have 1 divided by z to the minus 1, okay, which is also equal to the first term that I will not write again, plus z divided by volume, and then I have here 1 minus z. Okay. Well, the interpretation now is the following. This part comes from the continuum, whereas this part comes from the epsilon Q equal to 0 state, which is the ground state. So I can interpret this quantity, or if you want, since here I have volume, and 0 equal to z divided by 1 minus z is the number of particles in the state Q equal to 0. Okay? Because here is the density. Okay, the density gets a contribution from the continuum of the levels, or the particle, the number, number of particles is just this quantity times the volume. And since here I have isolated the term with epsilon equal to 0, and 0, I can define a quantity n0, which is equal to z divided by 1 minus z, which is the number of particles in the ground state, so in the epsilon equal to 0 state. Ok? Vediamo qui come sono messo. Allora, questo è 1. Questo è 2, ve l'ho raccontato. Ok, adesso faccio questa cosa qui e poi... Vabbè, no, sono ancora 38. Now, we will see, maybe not today, but next time, how to deal with the situation in which indeed I can have an occupation number, so a number of particles and 0 in the ground state, which is finite, so which is the limit in which z approaches, as we will see, 1 from the left. Okay. Yeah, you see from instance, you see already from here that if z is I don't know 1/2, for instance, well, or is a finite number, it's far from 1, but this quantity is finite, and therefore having here a volume, this quantity will drop to 0 in the thermodynamical limit. But in the case in which z is approaching 1 from the left, and we will see that it must approach from the left, well, actually you can see it already from there. Now I have here something that could diverge, and therefore the divergence, well, this quantity goes to 0 times volume can lead to a finite value, okay? This finite value will be the number of particles in the ground state, which is a situation that occurs indeed when z approaches 1. Okay, in normal situations, when z is far from 1, actually, these terms will drop to 0 because it's suppressed by 1 with the volume. Okay, so the situation, the pathological, let's say, situation is the one in which z approaches 1. And also, let me notice, at least at this level already, that we have some constraint on z from the interpretation that I got here. Now, this n0 being a number of particles in the ground state must be larger than 0. Okay, therefore, z divided by 1 minus z must be larger than 0. And this means that I have just an interval for z, which is the one in which z is between 0 and 1. Okay. So the fugacity is not free to have any value, as in other cases, but it must be limited within the range from 0 to 1. Okay, we will see that the case of the Bose-Einstein condensation would correspond to z approaching 1 from the left, because it must approach from the left. Whereas the classical situation will be the one, so the classical gas will be the one in which z approaches 0, okay? So those are the two limits, if you want. This is the classical limit, and here we will discover something new, which is the Bose-Einstein condensation. Let me go on until the pen is still working. Now let's forget about the Bose-Einstein condensation and this singularity, and let's make some thermodynamics. Let's continue with thermodynamics. Then we will see the classical limit, and then we will deal with the Bose-Einstein condensation. Okay. So for a moment, let's forget about Z approaching 1 from the left, which is the case of Bose-Einstein condensation. And let us consider again, so if you want the Z different from 1, okay, so no. So the way to write Bose-Einstein condensation usually is BEC. Okay, this Bose-Einstein condensation. In this case, as I said before, adesso scendo già a prenderlo. This additional term, which is the one corresponding to the ground state occupation number and the ground state energy, or the ground state contribution to the pressure, is vanishing because I have a finite expression multiplied by the 1 over B, and therefore I can just consider, for instance, in density, the continuum contribution, which was the following. Q, and I have a Q squared, and e to the non scrivo beta epsilon Q z minus 1 minus 1. Okay, so what we will do now is to work out a little bit this expression and to derive something in which on the left-hand side we have the dimensional quantities, and on the right-hand side we will have some function, some special function, which is the Bose function, with some mathematical properties that we will describe. So maybe let's stop already now, so to give me the time go downstairs, and we will continue after break. 5-10 minutes. Okay, so as I said before, let's forget about now the possibility to have a divergence which correspond to the case in which z approaches 1 from the left, and we will deal with this later. This is Bose-Einstein condensation. Now we will write in a slightly different way the density and the pressure, and this will be useful for the classical limit and also for studying the EC. Okay. So what I'm going to do is to write this equation in such a way to have on the left-hand side the physical quantity with the dimension of temperature, density, and so on and so forth, and on the right-hand side some mathematical function that will be the Bose function. So the thing is to write the variable x squared as b epsilon q, so beta epsilon q from here, which is 1 divided by kbt, and epsilon q is h squared, k squared, well, q squared in this case, right? Squared divided by 2n. Okay. Now, what is this quantity? This quantity, let me make it in such a way to have the lambda. Okay, so this is 1 divided by kbt. This is the h squared q squared divided by 2n. Then I have a 2 pi and another 2 pi coming from the fact that I have here h bar and here h squared. Now, kbt 2 pi and h squared are well, also the 2n, diciamo così che lo faccio in modo più serio, no, non capisce niente, 1 diviso kbt, and I have 2n, and I have h squared 2 pi, and q squared, and 2 pi, you can put everything, no? 1 kbt, 2n, h quadro, 2 pi, q quadro, e 2 pi di là. Okay, so now this should be equal to kbt 2 pi m h squared is the lambda, no? So lambda is h divided by square root of 2 pi m kbt. Okay, so here I should have a lambda squared, and then what is left? I have a q squared, lambda squared of q squared, lambda q squared, and then I should have the denominator a factor of pi and a factor of 4. Yeah. Let me check. Okay, so 2 and 2, one have another 2 goes in the lambda, and then I have a pi, which is left here. Okay. Then from here, I see that x is equal to the square root. I do the square root. X is equal to lambda q divided by 2 square root of pi. Okay. From this, dx is equal to lambda dq divided by 2 square root of pi. Okay, so by doing this, we can write this expression in a slightly different way. So now this is equal to 1 over 2 pi squared, which is still there. Then I have dq, so q to the power of 3 basically, which means 2 square root of pi divided by lambda to the power of 3. So 2 square root of pi divided by lambda to the power of 3. And yeah, and then I have the integral from 0 to plus infinity on the variable dx now of x squared divided by exponential of x squared z minus 1 minus 1 dovrebbe essere giusto dx x quadro z da meno 1 e poi c'è quello a fare lì davanti, ok? Which is still equal to 1 over 2 pi squared. Here I have 8 and pi to 3 halves, and here lambda cubed times the integral from 0 to plus infinity dx x squared e x squared z minus 1 minus 1. Okay. Now let me collect everything. Now here the quantity as dimension is the lambda here in the denominator. Here I have n. So let me write this in terms of the product, which is an important product, n lambda cubed. And here should be I should get just 4 divided by pi to the 1/2. And here I have the integral from 0 to plus infinity of dx x squared e to x squared z minus 1 minus 1. E questo dovrebbe essere una cosa. No, so now this is a much better way to write the relation between chemical potential and Z. And this expression is actually very useful also for doing the classical limit and the Bose-Einstein condensation limit that we will describe later. Okay? So for the moment, let's keep this expression just there, and we will work out a little bit more this later. So now let's do the same for the pressure. But first of all, I want to derive the equation of state and to show that actually the equation of state for this bosonic gas is actually, well, the relation between pressure and internal energy is actually the same that we had in the classical case. So let's start. Again, we are in a situation in which we are not considering Z close to 1. So I can just consider the continuum. So the expression for the pressure that we had before was this one, 0 to plus infinity, dq squared, and then I have a logarithm of 1 minus d into the minus beta epsilon q. Okay? 1 meno 2pi greco, q quadro, blah, blah, blah. Okay, so let's make the integral by parts. And I have a minus 1 divided by 2 pi squared overall. And here I have q. Let's consider this function here and integrate. So it's a q to the power of 3 divided by 3 times the logarithm of 1 minus z e to the minus beta epsilon q. This must be computed from 0 to plus infinity. And then I have minus the integral from 0 to plus infinity dq q q to the power of 3 divided by 3. Then I have the derivative of this quantity with respect to q, which is 1 minus 3 e to the minus beta epsilon q. And I'm doing the derivative of the log, then I have to derive this quantity with respect to q. So I will have a minus v e to the minus beta epsilon q. Then I have an additional minus beta factor, minus beta. And then I have the derivative of q with respect to q, epsilon q with respect to q. So let me write this for the moment as follows, otherwise I will not have space. Okay, so the derivative with respect to q of epsilon q. Now this term drops because in the limit in which q approaches 0, I have a q squared, a q to the power of 3. Here I have the log. I don't care about the log in any case, but in any case, this is finite because z is not close to 1. So this goes to 0. In the limit in which q goes to plus infinity, this quantity is approaches 0, and I can use the expansion of the log. Log of 1 plus x is x for x infinitesimal, and therefore I have an exponential suppression at q going to infinity of this integral of this function. So then I should have just the second term. Let me work out a little bit the second term. So I get the p divided by kbt is equal to, I have a minus here, a minus here, and then I have 2 minus there, so the minus will drop. And so I have a 1 divided by 2 pi squared, 1 divided by 2 pi squared. And then I have 1/3, which is in here, integral over the q squared, q cubed. Then I have, let me multiply by e to the minus beta h and divide by z as usual. And then I have an additional beta that I can also put outside. Here we'll have e to beta epsilon q, and I have a z to the minus 1, minus 1. And here, what is left should be just the derivative of epsilon q with respect to q. My epsilon q is h squared, q squared divided by 2m. So if I derive with respect to q this quantity, I get h squared q divided by m. Okay? Which is also equal, if I multiply and divide by 2, and I multiply by q, and here divide by q, it should be 2 divided by q times epsilon q. Okay, so this is 2 divided by q times epsilon q. Audace, questo qua, vediamo se è giusto. Yeah, should be correct. And so you see that here I can remove a kbt and this beta, and this drops in here 2, and so I have a p which is equal to 1 divided by 2 pi squared, and I have 2/3, and integral over dq 0 plus infinity of q to the power of 2 epsilon q, and here I have e beta epsilon q is e to the -1 -1. Ok? Uno sul 2π greco, 2 terzi, quell'affare là. Ok. Now, if you compare with the expression of the internal energy that we have derived before, this is just 2/3 the ratio between U and the volume. And so this is 2/3 U divided by the volume. So compare with the previous expression. Okay, so therefore we conclude that PV is equal to 2/3 U, as in the classical case. Okay, so the fact that we are considering a quantum gas does not modify the relation between pressure, volume, and internal energy. Okay. This is as the classical case, because in the classical case, what is U? U is written in terms of is 3/2 kBt times n, no? And whereas PV is equal to kb n t kBt n. Okay, so from this you derive the classical. So from the classical equation of state, you see that this PV is 2/3 U, as in this case of the Bose-Einstein particles, or the Bose particles. This 2/3 has to deal with the fact that, so it's correlated to the fact that we have 3 degrees of freedom, because we are considering particle moving in 3 dimensions. And actually, this index can be different by considering the case of massless particles. In that case, will be 1/3. And maybe we will show it as an exercise, or you can try to work it out. What happens when n is going to 0? So the case of a massless boson gas, for instance, the case of photons, you can consider the same expression as before, but that for in that case, epsilon q is not this quantity here, but for ultra-relativistic, or if you want, for massless, this epsilon q will be proportional to q and not to q squared. Okay, so you can, in that case, you will see that the coefficient factor in front of the PV, in front of the internal energy, is 1/3 instead of 2/3. Okay, so now this was the pressure. So the pressure, we say, is 1/2π², and then we have the 2/3 here, integral from 0 to plus infinity dq, q squared, epsilon q, e to beta epsilon q, z minus 1 minus 1. Now what we will do is to do the same as before. So consider the variable x, which was equal as before to dove che l'ho messo, q lambda divided by lambda divided by 2 square root of pi. And in such a case, the pressure will be equal to 1 over 2 pi squared. Then I have a 2/3. And then as before, now I have to count. Here you have a Q, one Q, two other Q, and then epsilon Q. I have two more Q, which is in total a power of 5. And when changing variable, I should get this 2 square root of pi divided by lambda to the power of 5. I'm computing the prefactor, okay? Let me see if I'm getting all the tests. It's okay. Then I have an additional factor here, which comes from this epsilon q. I have already singled out this q squared, but I have in any case h squared divided by 2m. Quello x, va bene. Yeah, and then I have an additional, so this epsilon q, yeah, okay. But then I have to consider that I have an additional factor there, which comes from the relation between beta and q. Okay. Allora, un attimo che mi perdo sempre con il fatto. This is fine. So as before, what we do is to say that x squared is equal to beta epsilon q, and so x squared is equal to 1 divided by kbt, and epsilon q is h squared q squared divided by 2m. So this is the x squared. So here you have considered just the relation. Okay, because I have singled out the q factor. So then I should have an additional h squared. Should have an additional h squared divided by 2m on kbt. Just a moment. H squared to m. Yeah. And then we have the integral from 0 to plus infinity of now dx. And here I had I can put now x to the power of 4. X to the power of 4. So one coming from this 2q squared and the other one coming from this 2q squared, but I have an additional 1 divided by 2m and the kbt to compensare. Okay? Questo è x alla quarta, then I have here x squared v minus 1 and minus 1. I think I have everything there. V minus 1, blah, blah, blah. and the prefactor is 1 over 2 pi squared, 2/3, quello alla quinta, e poi c'ho quella h tagliato quadro, 2m kbt. So because if you want here, I can derive that epsilon q is equal to x squared divided by beta. Epsilon q is so epsilon q is kbt x squared, and therefore I have to compensate this kbt. Okay, so this should be correct. Okay, I think it's correct. Now let me work out a little bit this prefactor. It's just boring, but one has to do it once in his life. Then I have here to the power of 5. Here I have h squared divided by, let me put a 2 pi here, m kbt. Then I have a 4 pi left. And then I have the integral from 0 plus infinity dx, x to the power of 4, z minus 1 minus 1. Vediamo se ho scritto bene quello. So I have the h squared, then I have 2 pi, which is 2 pi, one is there, and the other is 4 pi. And well, I consider also the factor of 2 here. Okay. So this should provide me another lambda to the power of 2. And with this lambda to the power of 5, I get again a lambda to the power of 3. So P is equal to ho fatto un po' di casino qua con questa cosa. Che BT deve stare sopra, infatti. Scusate, ho fatto un po' di casino qua. Sorry, let me repeat this because otherwise I'm not understanding. Okay. Sorry. It's just a matter of doing the substitution. It's not a difficult task. 0 plus infinity dq q squared divided by z minus 1 into beta epsilon q minus 1, and then I have the epsilon q. And epsilon q is h squared, scriviamolo qua, h squared divided by 2m, and then here you have a power of 4. Okay, and here you have a power of 4. L'h quadro diviso 2m sta lì. So then, as before, we introduce the variable x, which is equal to q times lambda divided by 2 square root of 5, from which q is equal to 2 square root of 5 divided by lambda, and here I have x. 2 square root of 5 divided by lambda times x. by lambda dx. So here I have 1 divided by 2 pi squared, and I have a 2/3. And then I have h squared divided by 2m, h squared divided by 2m. And here I have dq now is 2 square root of pi divided by lambda. And q to the power of 4 provides me another factor of this, but now this is the power of 4, so then it should have a 5 here. And now I get, yeah, so now I get integral from 0 to plus infinity, 0 to plus infinity of dx, x to the power of 4, d to the minus 1, e to the x squared minus 1. Oof. Okay. Mi sono dimenticato qualcosa? Should be correct, no? I think it should be correct. Due terzi h squared divided by 2m. Then I have the 2. Okay.
Non manca un KBT da
Infatti, no, sto perdendo quello. Ok, però si può fare così, credo. Aspettate un attimo, Now, okay, this is 1 divided by 2 pi squared. So, forse manca il KBT. Ah, eccolo dove stava il KBT. No, questo si semplifica di là. Sì, no, questo è giusto. Questo è giusto. Ok, just a moment. Two-thirds h squared divided by 2m. Facciamoci un KBT di qua, un KBT di là. And then I have this integral. Okay. So now, then it's okay now because I get a KBT here that I can put in the denominator of this principle if I want to, or I can leave there. And here I have lambda to the power of 2. Okay, so this 1 divided by 2 pi squared, 2/3, and then I have h squared divided by 2m kbt, and then I have 2 pi and another 2 pi, 2 pi. Then I have kbt. Then I have a 2 square root of pi divided by lambda to the power of 5. And also the integral which is still there. Okay. I think that now it's correct because here I get lambda squared at the numerator and lambda to the power of 5 at the denominator, so I have a lambda cubed. 1 over lambda cubed. Then a kbt left. Okay. Now it's a matter of working out the 2 and the pi now. The pi. So p is equal to 8/3. Un terzo rimane, ci dovrebbe rimanere un 8. 8/3 kbt. Then I have a lambda to the power of 3, because here I have lambda to the power of 5, and here lambda to the power of 3. Square root of pi is still there, and the integral from 0 to plus infinity dx, x to the power of 4, x squared minus z minus 1 minus 1. Ok, 8 terzi k dt lambda cube su f. Dovrebbe essere giusto così. Let me see just a moment. So if I have the correct numbers, the correct number of 2. So here I have these 2 and these 2 drops. Here I have 2, 2 and no, 1, 1, 2 goes in the lambda. I just have 4. And here I have 32 divided by 4, which is 8. So then this is the 8, this is the 3 here. Let me count the pi. The pi, I have a pi squared here. 1 pi, so I should have a pi to the power of 3 here, because the other one goes in the lambda. And here I have 5 divided by 2 minus 3, yeah, which is minus 1/2. So the pi is correct also there. Okay. So I think it's okay now. Okay. Sorry for that, but it's always a mess with the prefactor. Okay, good. So now let's write this expression in a slightly different way. Well, actually, no, let's leave it like it is. And let's write down also the similar expression for the density. Quindi questa la lasciamo così, the square root of pi, lambda cube, blah, blah, blah. And then we add, so this is an important relation, and a similar one for n lambda cubed, and lambda cubed, which was equal to 4 divided by square root of pi integral from 0 to plus infinity dx x squared e to x squared z minus 1 minus 1. Ok. 4 sulla radice di pi greco. Ok. So now let me call these two asterisks. And this is an asterisk. Now what I will do is to write this function and also that function in terms of a special function, which is the Bose function. Let me take this equation here and expand with respect to z. Expand around z equals 0, which will be very useful in the classical limit, for instance. So n lambda cubed, if I expand with respect to z around z equal to 0, of course this can be written as 4 divided by square root of pi, and then I have a z and integral from 0 to plus infinity of dx x squared ex to x squared minus e. Okay? So the first thing that I need to compute is the case in which z is approaching 0. So then I can write this as z, which is outside, and then I expand this expression around z equal to 0. So the first term will be, well, I can collect a z outside, and the first term will be a 4 divided by square root of pi integral from 0 to plus infinity of dx of what? X squared e to the minus x squared, because z is equal to 0 at the first order. Then I have second order. So this is actually the 0th order. First order in z will be a 4 divided by square root of pi. Then I have a z. Then I have to do the derivative and compute the derivative in z equal to 0. And if you do it, you get the following result. All the other terms. because when computing the derivative with respect to z, I have this function here to the power of 2. There is an additional -1, but then there is another minus to cancel. Then I compute at z equals 0, and then I get e to the 2x squared, which on the numerator becomes e to the -2x squared. And all the other terms are similar in the sense that when doing the derivative with respect to z, I always get a denominator at the power of 2, power of 3, etc. And computed in z equals to 0, I always get an abstraction like an exponential minus a certain number times x squared. And all these integrals can be done because they are basically the Gaussian integral, apart from integrating by parts. This is something I'm not going to do because it's boring. But then you can compute the terms in this series, and you get the first term is just 1. So this is equal to 1 if you compute it. And the second term is equal to 1 divided by 2/3 times z. So this is equal to z and times 1 divided by 2 to the power of 3/2, sorry, 3/2, etc. Okay? Now I'm writing upstairs the expression. So n lambda cubed in this series is z at leading order. Then I have a z squared on this one. Z squared divided by 2 to the power of 3/2 plus, then you go on z to the power of 3 and 3 to the power of 3/2 plus, etc. Okay. For the pressure, for the relation for the right hand side of the pressure equation, similarly, one gets a similar series that is again z at leading order, then z squared, and here we have 2 to the power of 5/2 plus z squared and 3 to the power of 5/2 plus all the other terms. Okay. Now it's useful to introduce the Bose function, which is the following function that we will use for the classical limit and for the Bose-Einstein condensation, which is the following. So this is the Bose function, which is indicated in gk of z, and this is defined as the sum from L equal to 1 and plus infinity of z to the power of L divided by L to the power of k. Okay, this is just a definition. You see from this expression that if I do the derivative with respect to z of gk, when doing the derivative, I get down a factor of L, and so we'll have k minus 1, and if I multiply by z, this is just k minus 1. Z times the derivative with respect to z of gk is jk minus 1. So this was an expression that we will use later, but it's better to write it down. Okay. Now, when introducing the Bose function, now the n lambda squared lambda cubed is just the Bose function with an exponent 3/2 there, or if you want the k, is equal to 3 half, whereas for the pressure, I have 5 half. Okay? So this n lambda cubed is g 3 half of z, and p lambda cubed divided by kBt, that was the relation of the pressure, is equal to the Bose function with an index which is 5 half. It's a much more compact way to write the relation, this one between density and chemical potential, which is hidden in the Z, and in the equation of state. Okay. We will see that also in the case of fermionic gas, we will have a similar expression, but with a Fermi function, which is very similar to this one, but we will see it later. Okay. Okay. Now, once we have this expression, it's easy to prove to make the classical limit, and then also to deal with the Bose-Einstein condensation. So let's try first of all with the classical limit. And the modification to the equation of state due to the fact that we are considering a quantum gas, which is a boson quantum gas, so symmetric wave function. Okay, let's keep this expression there. So first of all, let me remind you that at some point we wrote that n0 was equal to z divided by 1 minus z. This must be larger than 0, and therefore z is restricted to be in the range z from 0 to 1. What is z? Z is the exponential of beta mu, and therefore if z must be is in the range from 0 to 1, that means that mu is negative. Okay, so this two implies that mu is less equal than 0. For mu equal to 0, I get z equal to 1. For mu large and negative, I get that z is approaching 0. So in the case of a boson gas, the chemical potential is must be restricted to be negative. So it is a negative number. Okay. Okay. So now let me consider this expression, and lambda cubed. Now this is equal to z at leading order. When z is approaching 0. Indeed, this is exactly the classical limit, as we will see in a moment. Just a matter of seeing that n lambda cubed is equal to z, which means e to the beta mu, from which we get that the log of n lambda cubed is kBt is equal to mu, which is the classical gas. Okay. So if I stop at the leading order in Z, I get the classical relation between chemical potential and density. Okay. So Z approaching 0, in the case of bosons, but also for the case of fermions, is indeed the classical limit. Okay. Which correspond, if you think about chemical potential, corresponds to the case in which mu is large and negative. Or if you want, better to say that the product between beta mu is large and negative. Okay? So this is the case in which Z approaches 0, which is the classical limit. Now, of course, you see also from here, you can look at the other side. We always said that this number here provides somehow the limit, so the range of validity of the classical case, which is only when n lambda cube is a small number. No? That means small density or large temperature. Okay. So at leading order, you get the classical limit, you get the usual relation between chemical potential and the density and the lambda. Now we go on and see what is the first correction due to quantum mechanics to the equation of state, which is something that we have already done in the case of the correlation when considering the correlation of two particles, but now we can do something which is more systematic and start from this. So we said that, okay, let me start again, lambda cubed is equal to z plus, at the second order will be z power of 2 to the power of 3 half plus other terms that I'm not considering. So what I'm going to do is to consider the first correction as due to quantum mechanics. First correction to the classical case. Okay, so what I can do is from here, I can write that z is equal to lambda cubed n minus z squared and 2 to the power of 3 half. Now, let's substitute in this equation the first ansatz that we have from the classical case, which was the limit in which z is going to 0. So introduce now in the right hand side z equal to n lambda cubed, which is the classical result coming from function z. And so I get the z, it's a sort of way to solve this equation by iteration, by the iterating, okay? And then I have 1 divided by 2 to the power of 3 half. And here I have z to the power of 3, which is n lambda cubed to the power of 2. Okay? So which is then n lambda cubed, which can be collected. And here I have 1 minus 1 divided by 2 to the power of 3 half and lambda cubed. Okay? So z is equal to n lambda cubed, which is the classical case. Then, so with this 1. And then I have the first correction, which is a correction that goes as n lambda cubed to the power of 2 divided by 2 to the power of 3 half. Okay. Now, let's introduce now this z, which is corrected, which has in which we have considered the first correction due to quantum mechanics. Let's introduce this equation in here, in the relation between pressure lambda cubed, that was the following, that was z plus z squared and 2 to the power of 5 half plus etc. Now take this equation, let's call it 1 or A and B here, and put A in B. Okay. So now we get that P lambda cubed KBT is equal to Z, which is this guy here, plus the same guy to the power of 2 and divided by 2 to the power of 5 half. Ok, vabbè, se fai questo, ok, so one gets n lambda cube, vediamo se l'ho fatto in modo furbesco. no, vabbè, mettiamolo così, 1 divided by 2 to the power of 3 half, n lambda cubed to the power of 2, where here's just d. Then I have another term which is 1 divided by 2 to the power of 5 half. And then I have b squared, but at leading order in n lambda cubed, I just keep the n lambda cubed square term. Plus all the other terms. Ok, fatemi controllare che c'è giusto. Un terzo n lambda cube squared. Okay. Because then I have all the other terms, no? Because here we'll have, sorry, I'm substituting these into this expression. So the first order is n lambda cubed squared. Then there will be an n lambda cubed to the power of 4. And then there is an n lambda cubed times, so it's n lambda cubed to the power of 3, because you have to do this, yeah, because you have to do this guy, the square of this guy. Quadrato di quello 1, quadrato di quello e quello. Dovrei avere un altro termine così. I think it's correct. So let me check if I have the terms. Okay, so now it's a matter of doing the calculation here. And here I get that P lambda cubed divided by KBT is equal to an n lambda cubed, that is the leading term. And then you get minus, if you do this calculation, I have to do 1 divided by 2 to the power of 5 half minus 1 divided by 2 to the power of 3 half. And if you do the calculation, you will get lambda cubed n squared divided by 2 to the power of 5 half. Devo spiegare che sono le 11. N lambda cubed, e questo qui al quadrato, diviso quello. Okay. Now I can remove a lambda cubed from here, and P divided by KBT, P divided by KBT is equal to N minus, then I have N N squared lambda cubed, and here I have 2 to the power of 5 half. Then let me divide by N to get it better. Need the final formula. P divided by NKBT is equal to 1 minus N lambda cubed to the power of 5 half. Okay. So which is in the equation of state, this is the classical gas, no? So this is the ideal gas. Then the first correction is the negative correction, which corresponds again to the fact that this is a Bose-Einstein boson gas, and bosons like to be feel a sort of effective attraction, as we discussed last time. Okay. So the pressure is reduced by this factor here. Okay, so this is an effective attraction between bosons. Okay, that basically reduces the pressure as compared to the classical case. Okay. Whereas in the case of fermions, we will see that it's just the opposite. So in the case of fermions, we will get an effective repulsion that comes from the fact that fermions do not like to be in the same place. And therefore, we will have an effective repulsion. Sorry for being late. Let me close this.